All right, final video for Module 7. This is CIT 1121, Module 7, Submodule 4, Switch Speeds and Forwarding Methods. Switch speeds first. Actually, no, that's totally wrong. Forwarding methods are first, even though it's called switch speeds and forwarding methods. We're going to do the forwarding methods first, and we'll do the switch speeds second. So let's do some forwarding methods. The main two forwarding methods, or actually the main forwarding method, the normal one that's used, is something called cut-through. And if you want to look at the definition there, it says the frame forwarding method forwards the frame before it's entirely received. At a minimum, the destination address of the frame must be read before the frame can be forwarded. So, in a cut-through system, we're going to read just part of the frame. So, what does this do for error correction? The answer is nothing. So, the default process for forwarding frames is that we do not check for errors at the switch. We'll leave that to the receiving device that's going to pick up that information. Now, we're going to draw a PDU. And this PDU, we're going to do we'll do the frame header on the left-hand side, right? So we're going to do frame. Man, the drawings are getting worse as the morning goes on. Frame, packet. Let's just start over. That's too awful. I'm sorry I'm wasting your time. Okay, let's try that again. Frame, this is not built to scale. It's just for, so it looks cool. Frame header, packet header, segment header, and data, right? And at the very end, we're going to do our CRC, our frame check sequence at the very end. So let's look at these two methods. Now, if the information is accepted by a switch, as a switch receives this, it is just a stream. Once again, it's a stream of binary information. It's just a bunch of zeros and ones. And inside that frame header, the frame header has three fields for 802.3 header. It has a destination MAC, right? That is part of it. Destination MAC is part of the frame header. And there is a source MAC address. And there is a field called the type field, and that is it. Those are the three absolutely, positively, absolutely have to have necessary fields inside of the frame header. We'll deal with the start of frame delimiter and the preamble in another slideshow. But for now, this is what we've got, right? So if we're going to do cut through, how much are we going to read of this particular protocol data unit? The whole thing's going to go through the switch. It's got a source, it's got a destination, it's data that needs to be processed someplace. How much is our switch going to read? And it says here it must read, the frame must be read before the frame can be forwarded, at least the destination address. This part right here, at least the destination address has to be read. So as this frame gets accepted, the first 48 bits in the frame header have to be read, and that is your cut-through method right there. You're going to read that destination MAC address field. We're going to go over to the CAM table. We're going to find where that destination MAC address resides. We're going to associate it to an interface, and we're going to forward this thing out, and there it's gone. That's it. All right? Now, if you're getting a whole bunch of errors on your network, there are things that are not working correctly, and you find that you're getting missized packets or frames, sometimes known as, we call them runts. The small ones are called runts. The big ones are called giants. What you might want to do is start checking to see, before you forward this off to its destination, you might want to check and see that it's actually about the number of bytes that it's supposed to be. So once again, if we looked at this whole thing and we said, yeah, this is from here all the way over to here is about 1,500 bytes. It's about 1,500 bytes. What we're going to do is we're going to read all of this, and then we're going to check that CRC, that frame check sequence. And if it says, about 1,500, close enough, then we'll send it through. And if it comes back and it's like, it's about 750, then we'd say, you know what, let's just drop it right here. Let's not even forward it to the destination. Or it's about 3,000. No way. No, something's wrong. it's supposed to be 1,500, and we actually counted 3,000 or 750 or a number that's not even close to 1,500, we're not going to forward it on. We're just going to stop it right there. But the default process, by default, we're going to use cut-through switching as our method, and we're going to assume that we're not going to see any errors. Why? Because it's faster. Why read this whole thing? Why count up to 1,500 when you can just count to 48 and check that and then forward it on? That's faster. So that's why cut-through is the preferred method. Okay. There are two other methods. One of them is called fast forward. We'll get into that later. And fragment free, which we read a little bit more. But for the most part, the main two that they're going to be concerned with are these two here, store and forward and cut through. All right, good. Let's go ahead and move on to the next slide. And it gets into the idea behind memory buffering on a switch. Now, here's the thing. A switch's job is to move information from one interface to another interface. And it will provide a collision-free environment. Now, before there were switches, there were hubs. And if we had two devices and at the exact same time wanted to send information either to each other or to another device, there's a possibility that the information, the electrical modulated waves that enter into the hub, could interfere with each other, which would cause all of the communications to cease. And that's what's called a collision. The collision were monitored by the network interface cards, and if they identified a collision and they had just sent something, the cards would go into a reset mode, and they would identify that whatever they just sent didn't make it, and then they would wait a random period of time, and then carrier sense again, and if the line was clear, they would try again. And that was the process that was used. Now, when switches became part of the network fabric, that was all gone. The switch was now had a small processor brain, which could build that CAM table, and in addition to the CAM table, it could also warehouse or buffer information for a particular interface. So let's give you an example. Device A and device B both want to send information to device C. Device C can only accept information as fast as it can accept it. So what's going to happen is this, is A and B both send information, and the CAM table is read, and the same destination MAC address at the very same time is identified, and the traffic goes to get an order, and it goes like that, and the switch then says this, whoa, 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 this information's about to collide. Wait, let's do this. Whichever one of these interfaces has a lower number, you get to go first. And whoever's got a higher number, you get to sit, and you can sit in memory, and you can wait for the other one to go through, and then you can go through. And that's how it works. Now, depending on the switches that you purchase, they may have memory that's based on the port. So every given port has X amount of memory. Now, this is okay. It's good that you have memory because it's going to stop the old process, which had collisions. But port-based memory could possibly run out as well. So if a specific interface is constantly being accessed, like a server interface off of the switch, if there's so much buffering that has to happen that we run out of port-based memory, then we just start dropping packets. And as you probably don't know yet, but it's coming, dropped packets really affect your life. When packets start getting dropped, things start working slower, more triple tickets get opened, more work you have to do. So we don't like that. So what we could do is buy a better switch, a nicer switch, that has shared memory, which says this, there's a lot of memory on this, and we can carve out the amount of memory space that we need on the total memory. So for 20 of these interfaces, there's never any buffering. But on one of them, there's a lot. So what we can do is allocate all the memory that we would have had port-based on 20 or 21 interfaces and point it all towards the shared memory of one of the interfaces, and then it would create more, and we would definitely have less dropped traffic. That's all they're getting into on this. Okay? So that's that. Two more slides. The last couple things. Full and half duplex, we already spoke about this. In a switched environment, you're going to be working in full duplex all the time. There was a time when there could have been collisions, and like I said, some of the interfaces on the device were designed to listen for collisions. So of the 8 little wires that's inside of an RJ45 jack, 2 of them used to be used to just listen for collisions. That was their job. They would identify a collision based on a drop in voltage on the line, and if that happened, it would alert the network interface card that there was a drop in voltage, which means that you lost your data, which means you had to run that back-off algorithm that we talked about a few minutes ago. It doesn't happen anymore. Pretty much everything is full duplex now because there are no more collisions, because switches have enough of a brain to figure out how to organize the traffic through memory and a CAM table to make things actually work. So keep that in mind. So it'll always be in full duplex from here on out. And then the last thing is something that gets into a whole other can of worms that we're not going to get into in this particular presentation. But it talks about a technology called AutoMdix. And AutoMdix is a concept that says this, that there are different types of network cables. There is something called a straight-through cable, and there is something called a crossover cable. And we'll spend more time on this a little bit later when we start talking about these differences between these. But the idea is this. In a straight-through cable, all of the 8 little wires that are inside of that Cat6 cable are pinned out in pins 1 through 8 exactly the same way on both sides. So the information that is being placed on pin 1 on one side of the cable ends up leaving the cable on pin 1 on the other side. Anything that's put on pin 2 ends up leaving on pin 2. The crossover cable says this. We're going to switch some of those around. We're going to maybe say anything that is sent in on pin 1 is going to end up on pin 3, and anything that comes in on pin 2 is going to end up leaving on pin 6. Now here's why. Because in a regular Ethernet jack, in a regular RJ45 jack, most devices are going to TX send, and we'll make it less complicated later. TX or send, that's right, send on those pins 1 and 2. All right. Now, if we're sending into another device, like a computer, if it always sends on 1 and 2, and we send a straight-through cable, it's going to get received on pins 1 and 2, and that's not where it's looking to receive things. So the receiving, called RX, or receive pins, are going to be pins 3 and 6. And we can expand this later, but don't worry about that. So receive pins are 3 and 6. So if we take what's sent on 1 and 2, and we send it, and we just cross them over inside of the wire, and they leave on 3 and 6, we've made what's called a crossover cable. And a crossover cable is important for devices that have no intermediary device in between them. So in general, if you have a PC and you want it to connect directly to another PC, you would use a crossover cable. If you have a PC that's connected to a switch that's connected to another PC, you would use a straight-through cable because the switch is designed to listen on pins 1 and 2 and to send out on pins 3 and 6, thus the switching of the information. So it comes in on 1 and 2, we move it over to 3 and 6 on the way out. It happens automatically, so you use 2 straight-through cables. But you can replace those 2 straight-through cables with a single crossover cable by having the pinouts of pins 1 and 2 come out of the other side of the wire on pins 3 and 6. Once again, we'll do a whole thing on this one, get a RJ45 jacks and so on and so forth. Now, here's the thing. This can be complex. And what AutoMdix says, and that's the only thing that why we have this, is kind of just got thrown in here. AutoMdix says people are dumb. They can't figure out straight-through and crossover cable. They don't really know how it works. So we're going to run a little program on our interfaces. And if somebody plugs the wrong cable in, somebody plugs a straight-through cable where they should have plugged in a crossover cable, we'll just switch the pins programmatically on the other side, and it'll work anyway. And if you plug a crossover where you should have had a straight-through, same thing. They'll just figure it out on their own. AutoMdix has been around for quite a while. Keep in mind, though, that a lot of networking equipment has been in service and been in service for over 15 to 20 years, and AutoMdix was not a function for a very long time. So you may sometimes be able to use a straight-through where you're supposed to use a crossover, and you may sometimes be able to use a crossover where you should have used a straight-through, but it isn't always going to work. And the reason for that is that AutoMdix. So keep that in mind. And you should really, and we'll do, there's another presentation where we go through this whole thing on straight throughs versus crossovers. But for today, this is it. This is the last for Mod 7.